Calculus, welcome back. We are going to talk about 6-2 today. So if you have any questions on 6-1, feel free to email me or make a video of you doing a problem, or send me a picture of your work, whatever you want to do. Okay, so 6-2. The topic is called solids of revolution. Now, whether or not we do any math in this first video, I don't know. We'll see how long it lasts. But we're going to start just about talking about the concept of a solid of revolution. Okay, let me start. I'm not even going to draw anything remotely mathematically related. I'm just going to draw a line. And I guess that's sort of mathematically related. Okay, now I want you to envision this line that I drew as kind of a really thin steel beam, okay, that just kind of runs. It exists in three-dimensional space there, okay, but it's just a very thin steel beam just out in space, kind of like this pen, okay, or this pencil. Okay, now the next thing I want you to envision is a wooden board, okay? And I'm going to attach that wooden board to that steel beam. And then I'm going to take that wooden board, and it's attached to the beam there, but I'm going to spin it around and around and around, okay? As that board spins around, okay, it comes out of the page, it goes into the page, it goes back behind the page. It's in three-dimensional space, and it's just spinning, 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 spinning around that line there. It's going to carve out some space. And in fact, if you spun it fast enough, what would it think about what it would look like. Well, I mean, it should look like a cylinder, right? A cylinder that is kind of on its side, like a can is a cylinder. This would be like maybe a tuna can, right? A tuna can on its side. Okay, so as this board comes around, it carves out space in 3 dimensions, and the solid figure that it would probably represent the best, or be represented by the best, is, say, a tuna can. Okay, now I'm going to erase, well, maybe I won't even erase it. I'm going to draw a second board, this time a triangular board. We're going to attach that to the same steel beam, and we're going to spin it. Spin, 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 spin. Eliza, what's that going to look like?
A cone.
That will look like a cone, yeah. It'll be on its side, but if I turned it upside down and put it on the table, it would look like a cone coming up out of the ground. Okay, very good, Eliza. Okay, now, that's great. Let's take this to the next level. And again, we're not doing any math yet, are we? Let's take that same steel beam, and this time, we're going to draw a board up there, above the axis of revolution. And we're going to spin it around. Okay, it's going to stay the same distance from the beam as it comes out and around and then back, and it's like a board going around and around this pen or this pencil. Okay, what shape will that carve out in 3-dimensional space?
It's like a donut, kind of. Like a squarish donut.
A squarish donut. Okay. Remind me to order one of those next time I go to the donut store. Okay, but you know what? Though she's almost right. And if instead of putting a square up there, I put a circle, and I spun it, Eliza, what's it look like now?
A donut.
Now it looks like a real donut, not a squarish donut. Okay. Everything that we've talked about has been what's called a solid of revolution. It's a solid a solid of revolution is a solid created by revolving an area around what's called an axis of revolution. This steel beam here is serving as the axis of revolution. And then if I take a square area around it, I get a squarish donut. If I take a round area around it, I get a regular human donut. Okay. Now, let's continue here. Now, what if I do this? What if I do something like that and I spin, Eliza, what would this look like if I spun that around?
Is that supposed to be a
It's a rectangle.
Oh, well, it looks like a.
What would it be, smart girl?
A rectangular-ish donut.
Yeah, but come on, we can do better than that.
Yeah.
What's something that, is kind of flat, kind of thin, but it's got a hole in the middle?
A frisbee with a hole in the middle.
A frisbee with a hole in the middle. See, Eliza doesn't know what a washer is, okay? But, here in the United States, we call those washers, okay? It's like a coin with a hole in the middle, okay? Anyway, that's another solid of revolution. Now, solids of revolution can have like all kinds of weird shapes and such. We've talked about some really basic ones here. But now let's get, this next one's going to be the simplest one I've ever drawn. This time, instead of drawing an area attached, I'm just going to draw a line, or a line segment, attached, and that line's going to spin around the axis of revolution. What kind of a solid is that going to make, Eliza?
Like a circle type thing.
A circle type thing. Do you know what we call that?
A circle.
A circle, okay, yeah. Not bad. Think
Does
about
the
real.
line have any width to it?
That's a great question. Well, the way I have it drawn, on paper, it looks like it has width. So just think of something in real life that would look like what you get. She's making like a coin would be a good example here. Okay, a coin.
A coin has width.
I know a coin has width. Yeah, and so does this. But Eliza, that's very astute of you to notice that really a line segment doesn't have any width. And so if I spin this around, we get what's called an infinitely thin disk. Okay, a disk is like the thinnest possible thing you can create with a solid of revolution. Now, if instead of making that line segment be attached to the axis of revolution, if I put it up here and I spin it around the axis of revolution, now we're talking about an infinitely thin cylinder. No, what about that?
Disc with the hole in the middle.
Yeah, okay. I totally misspoke there. It's not an infinitely thin cylinder. That's what I would have had before. An infinitely thin cylinder or disc. You could say either one. It'd be an infinitely thin washer. Okay, remember it's a flat, round thing.
Donut.
Well, now a donut would have.
No, a flat, round donut.
Okay, so if you took a donut and you pounded it out till it was infinitely thin,
yes.
I suppose that's what you'd have, right? Okay, that's another solid of revolution. Now, the thing is let's start with a disk. Or, I've used the word disk a couple of times here. And disk is a really great word. But there's a word that I prefer, and that is cylinder. Okay, now you may be saying, well, if cylinder has thickness and the flat disk doesn't. But let's think about this. Okay, I'm going to draw another line segment right here. And I think we'd all agree if that is infinitely thin and I spin that around, I get a really flat disk. But what I'm going to tell you, what I'm going to call this, is I'm going to call that an infinitely thin cylinder. Okay, now, let's talk about the volume of that cylinder that we create by spinning this around here. Now, well, to find the volume of a cylinder, Eliza, do you know how to find the volume of a cylinder?
Yeah.
You want to tell me?
We find the area of the base.
Base, okay, and the base is what shape?
Circle.
So the area is?
Pi r squared.
Pi r squared, okay. Pretty good. And then what do you do after you find the area of the base?
You multiply that by the height.
By the height, okay. Now, it can be slightly confusing, because remember this cylinder is turned on its side, right? So the height is actually the horizontal distance, right? And Eliza, how wide is that going to be?
within.
Very good. That's exactly right. And those of you at home know that that is when an infinitely thin width in the horizontal direction is denoted dx. Okay. Now I wrote it really small. Can you see that? Okay.
I think so. Yeah.
Okay. That's a dx. That's an infinitely thin increment in the horizontal direction. Okay. Now, so the area of the circle created when we spin that around, the area is going to be pi r squared, and then we take that times the height, which is dx. Well, okay, so let's talk about the area then. Well, the pi, which is just going to be a pi. But radius, well, the radius of the solid created is just going to be whatever this is right here, right? So let's call that distance. Now you're going to see where I'm going here. I'm going to call that distance f of x. Okay, remember f of x can be used pretty much synonymously with a y value, and that is a y value. If this is okay, spoiler alert, that's the x-axis for right now. Okay, and so this is the distance from the distance from this point to the x-axis. We'll call it f of x or y. So the volume of that, and I'm going to use a subscript here, v sub cylinder is pi times the radius squared times the height, which is dx. That's the volume of the cylinder created by revolving that little line segment around the x-axis. Eliza, how are we doing on time?
11:51.
All right, let's pause that, and we'll come back a little later.